Hi guys, how's it going? Today we'll be going over Riemann sums. We'll go over right Riemann sums, left Riemann sums, and we'll go over mid Riemann sums. And we'll go over a problem with trapezoidal sums to sum it off, and we'll go about the concept behind Riemann sum, why it's useful, and all that stuff. So without further ado, let's get started. So first, what is a Riemann sum? Really, we use a Riemann sum. Let's say we're gonna have a point from A here, B here, C, D, and you want to know the area underneath this curve. At this, like, what is this area and what is this? Now, since these are linear, we could make a trapezoid. But if these were a little bit curved, we can also use trapezoid as well to get an approximation. But the idea behind Riemann sum, left, right, and middle, would be to make a series of rectangles to be positioned under the curve to give us an approximation. And so there's three different ways that we can draw out this triangle. Let's say we want to divide into two subintervals. Left Riemann sum I'll have in blue, starts at the left endpoint and draws like that. That would be one of your rectangles. Sorry, I might have said triangles before. And then the second rectangle would be right there. And that would be our left Riemann sum on this point, because we start from the left and we go out to the middle toward delta x, which is right here. And that would be the first rectangle. That would be the second rectangle. If you start right here and right here, it'd be something very interesting. But we'll cover that a little bit later. That's a left Riemann sum because we start from the left endpoint, we draw it out to delta x, and then bring it down, and that'll be a rectangles. What if you did a right Riemann sum? If you did a right one, draw out from the right, and we come down. And do it one more time. Since this is right endpoint, or right here, and come down. Okay, so there's a difference right here, and same here. There'd be your one rectangle and the second. Now, we could see something that's very intriguing, and something that's very worth noting is that whenever a function is decreasing, let's say over a and b, because this, we'll call it f of x, fx is actually decreasing, or increasing, sorry. I'm looking at it this way, we should probably be looking at it this way. When it's increasing, our left Riemann sum will be matching up at a lower point and coming out inside of it. So we're not accounting for this area right here. And so because of this, we will have an under approximation of what our actual area underneath the curve would be. Erase that a little bit. And same value here for the when f of x is decreasing, the right Riemann sum will be as well an under approximation, because once again it's not accounting for that area right there. And if you look at it, the other way is possible. When the function is increasing, the right Riemann sum will be an over approximation, because you start from the right and we draw to the left instead of drawing from the left to the right. And so we're accounting for all this extra area right here. And for when it's decreasing, we have the left Riemann sum being an over approximation. So that's something that's very worth noting. And it's kind of an interesting relation. Now, that's cool and all, but if you want a somewhat more kind of precise estimation, we could try to do the best of both worlds and do a middle. So we'd go between A and B. So we'll call this like just x right here. And from x right here, we'd take the height there. And then we would draw from the left right here and from the right here. And so that way we see that we are over approximating on the left side here, but we're under approximating on the right side. So it kind of balances out somewhat. It won't always be exact. And it will not be, in fact, a lot of times it is still an approximation. Very few times it would actually be an exact solution. So we're still approximating here. But when we do the same thing here, we see that there's not a clear-cut case like we have with the right and left Riemann sums, where when it's increasing, it's an under approximation, or etc. So that is another way that we could do it. really we would take 2 points or 3 points. We'd have the middle one, the middle point. If we had it on this table, we would have 2 points, take the middle point, and then find a way to use the 2 on the sides and split it out. So that's all cool. But what I want to be interested in is this problem right here. So those are right, left, and middle Riemann sums. What about trapezoidal Riemann sums? Now, I have the table right here full of data, and they want us to take the trapezoidal Riemann sum from 2 to 10 and divide it up into 4 different subintervals. And so I just drew a line through it to show us that it will be very similar to this. With trapezoidal Riemann sums, we take a point from the left, point from the right, draw down, and then connect those 2 points like that. So that would be our first trapezoid. Second trapezoid would be this point right here, this one right here. Connect them, bring it down, and that'd be our second one, and so forth. And so we would have 4 different trapezoids right there. And so when we go to calculate this, we have to use the area of a trapezoid, which is base 1 plus base 2 over 2 all times the height of a trapezoid. So that would be the area of a trapezoid. But when we look at it in this scenario, we would have, so these 2 would be the bases because that's one base and that's the second base, and this would be the height. So base 1 right here would be the first y value, so it would be 1.5 plus 2, which is the second base, divided by 2 times the height, which is the difference in x, times 1. Plus this trapezoid, this trapezoid, and this trapezoid, which I'll calculate right here. So using the same logics, 6 plus 2 over 2 would be our average, right? That base, and then multiply by that, then we multiply by the difference in x. So that would be 5 minus 3 is 2. Plus this one right here, same thing, y values are going to be 6 and 11. So 6 plus 11 over 2. And then times 7 minus 5, which is 2. Plus 5 plus 11, 15, sorry, plus 11. Divided by 2. And multiplied by the height. So 10 minus 7 is 3. And at that point, it's just plugging into a calculator and boxing the answer. But I'll leave it in this form. But really, it's the same thing if you were to calculate a left or right Riemann sum. But with the trapezoidal Riemann sum, it's a little easier to see on a graph than it is from a table. This is why I drew out the graph. Normally, we just get in a table. But once you start picking up on the patterns they give you, it starts becoming a lot similar. And we could start writing out. They will introduce you a equation with summation of something delta x with x sub I with an I index to n, something like that, and there's n subintervals. I'm not going to go over that right now in this video because at this point, the more conceptual side is more important, and the more you test it on this, because after we can apply this to many different things. For example, this problem could be time and then the height of a tree and then the average height of a tree through time, etc. could be deduced by the area underneath the curve. So that would be another way. But the main reason why we're introduced to Riemann sums right now in calculus is because they're very vital for what we're going to do next, which is we have a curve. Say this is f of x. I want to find from A to B. I want to find the area underneath this curve. A main thing that you will see is that the more subintervals you have, let's say the more rectangles that you have underneath the curve, the more precise your measurement will be. And so, let's say we had an infinite amount. it will give us a very, 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 very close approximation that we can mistake as the right answer. And when we do that, that's when we write the integral from a to b from our bounds of f of x, the function dx. Dx kind of just caps off the integral, shows what you're integrating. And so this Riemann sums are really just an introduction to integrals. And really, integrals are just an infinite amount of Riemann sums taken over a certain place. And this is why we're introduced to them in calculus right now. I hope you found this video helpful and useful. Please leave in the comments down below what you would think would be more useful moving forward. Hope you enjoyed. Thanks for watching.